Good morning, good afternoon, good night, everyone. I'm Valentina, I'm the YESS officer. And today is a special day. We are having our first webinar for the North American region. And in this occasion, we are having two speakers from this region, Thomas and Zack. They will be presenting about their latest research. So before we move forward to this part, I will just read you the code of conduct that we always have in our webinars. Please be polite and respectful to the speakers and to all the participants here. If you have any question, please type it in the chat box and write the name of the person you are asking this question to. Can be Thomas, that will be talking first, or Zack. And then during the Q&A after the second presentation, we will have time for replying the questions. In case there is any question that it's we don't have time to do it, I can send the questions to that speaker and then forward the reply. And everything in this meeting, in this webinar, the presentations and the chat box, everything has been recorded, and I will upload the recording to YouTube in the upcoming days. So if you want to check it again or have anything that it's interesting for you or for your work, you will be able to watch it again. So that's everything from my side. I will now give the floor to Hodon. She will introduce the first speaker.
Thanks, Valentina. I will be introducing Thomas. Thomas is speaking first. Thomas is a hydrologic and hydraulic engineer specializing in 1D and 2D modeling using HEC-Ras and HEC-HMS. He has a decade of experience in the water resources sector, earning his master's degree in water resource engineering from the University of Texas at El Paso. During his career, he dedicated 4 years to serving in Rwanda, Africa, as part of an Indian mission to enhance agricultural exports in the Southern African region. He is a project manager currently at Consor Engineers, leading a team engaged in floodplain mapping and mitigation projects. So with that, I'll hand over the floor to Thomas to talk about his research.
Hey everyone, I'm gonna share my screen. Hopefully everyone can see it. So my name is Thomas Poulose. I work as a water resource manager, specialization in hydrology and hydraulic modeling. Currently based in Houston, Texas with Consor Engineers. I'm excited to join this webinar, share my knowledge with all of you. During my presentation, I will delve into the advanced terrain modification tools available in the latest version of HEC-Ras. As many of you may be aware, HEC-Ras recently released version 6.5, so I recommend using HEC-Ras 6.4 or higher for these modifications. Going to the next slide. I'll be introducing to the HEC-Ras Mapper terrain modification tool for hands-on terrain editing with RAS Mapper without needing third-party license like ArcGIS. We'll cover cloning terrain files, modifying layers, removing culvert crossings, modeling detention basins, applications, and address any questions that you have. HEC-Ras is a software developed by the U.S. Army Corps of Engineers. It's widely used for hydraulic modeling for various water resource engineering applications. RAS Mapper is a graphical user interface within HEC-Ras, which facilitates modifying and visualizing hydraulic model geometry and results. You can download the HEC-Ras software from the link here. So first, introduction to the RAS Mapper modification tool. To start adding a modification layer to the terrain in RAS Mapper, the first step is to create a clone of your terrain. This clone generates a virtual copy of a terrain within the same terrain folder. RAS Mapper then generates a HDF file for the clone, which maps to the same raster as the original terrain. To create the clone, simply right-click your terrain and select Clone Terrain Virtual, which will prompt a dialog box to enter the clone's name. In this example, it's named Modified Terrain. Once created, you'll notice the Modified Terrain clone appear as the new terrain on the right. Creating a clone ensures you don't alter the original terrain, allowing you to compare modification with the original to ensure they're effective. This step is crucial before making any terrain modifications. Moving on, let's discuss how to add a modification layer to the clone terrain. Simply right-click on the clone terrain and select Add Modification Layer to begin your first modification. Within this feature, you'll find a range of shape and functionality options to choose from, which we refer to as the different modification tools available in RAS Mapper. Each tool serves a unique purpose and can be used individually or combined to achieve desired results. Due to time constraints, we won't cover the functionality of each option in detail. Instead, this presentation will focus on the tools necessary for terrain modification, specifically for removing culvert crossings and modeling detention basins. These tools primarily involve the multi-point polygon, channel, and high ground options. Now let's explore how the terrain modification tool can effectively remove culvert crossings within the terrain. As shown in this image, the terrain currently includes a culvert embedded within it. Running simulation with such terrain would yield inaccurate results as the culvert obstructs the flow in the channel. Typically, removing the culvert involves a cumbersome process utilizing multiple third-party applications like ArcGIS, which require licensing. To initiate the modification, begin by drawing a line using the modification tool. Once the modification line is added to the desired location, right-click to edit parameters such as side slope. In this instance, a side slope of 0.001 for both left and right creates a vertical wall. Use the lower terrain value as a modification method. Additionally, a width of 20 feet covers the entire width of the culvert. So when you cut a cross section, it illustrates the terrain at the culvert location and this at the downstream. And notice how the channel opens up, promoting flow continuity. This improvement is crucial for accurate simulation as demonstrated in the following slide. Depending on your requirement, you can adjust side slopes such as 4:1 or 3:1 and specify desired width matching the culvert width. Here we have a before and after images showcasing the water flow in the channel. On the right, after opening the channel, you'll notice improved connectivity between upstream and downstream area. This alternation will impact water surface elevation results. But the difference may not be substantial in narrow channels like this. It's crucial to consider for wider and larger channels before simulating the model. Now let's explore achieving the same outcome using the polygons multi-point tool within the modification layer. By right-clicking the modification layer and selecting Add Modification Polygons Multi-Point, draw a polygon as depicted in the left image. Next, while in edit mode, right-click the polygon file and choose the option to create control points along the polygon profile. This action generates points along the polygon boundary. And now let's examine how we can adjust these control points to effectively remove the culvert barrier from the terrain. The control points created can be adjusted to eliminate the culvert barrier from the terrain by adding additional control points above and below the culvert and removing that is not needed. So here you can see an animation of how the control points are being removed to smoothen the terrain and remove the culvert crossing here. Once the desired configuration is reached, so then you can draw a section across the culvert and one at the downstream to see the difference. So you can see both have the same kind of cross section. So you have removed the culvert crossing here. You can also individually change the elevation point of each control point, which is further refinement to this modification. Here are the before and after results of the modification. On the right, you will notice improved connectivity between upstream and downstream areas. Now let's explore how to model a detention basin using the terrain modification tool within the RAS Mapper. The initial step involves identifying the optimal location for the basin. This involves reviewing existing scenario, runs to pinpoint where water can enter the basin from the main river. Additionally, assess this location for potential inflow and outflow from the basin. Next, determine the ordinary high water mark in the channel near the basin. This can be determined based on existing gauge in the area. Once the high water mark is established, determine the boundaries of the parcels in the area where the detention basins will be located. Using the average existing ground elevation and the ordinary high water mark, calculate the maximum depth of the basin. This depth may vary based on regulation. For example, I have used a foot above the ordinary high water mark as a regulatory measure to determine the maximum depth of the basin. With the depth and required volume in mind, determine the basin's total area. Based on this area, create a polygon in the vicinity to represent the detention basin. So in this webinar, we will cover two types of detention basin. First, we'll discuss how to model a wet bottom basin, followed by a demonstration converting it into a dry bottom basin. For the wet bottom basin, the terrain modification process involves 4 components. We'll create modification layers in the following order: bottom elevation, 4:1 side slopes, and inlet weir. Additionally, the outlet structure will be developed using 1D, 2D geometry. As mentioned earlier, the initial step is to designate the area where the basin will be modeled. Here, I'm utilizing the existing floodplain raster to determine this location. Here, the water is entering the basin from the river at the location indicated by the arrow. On the right side, I'm establishing the bottom elevation depth of the basin by creating a section across the river and existing ground where the basin will be modeled. The average elevation of the existing ground in the area is 17.5 feet, and the assumed itinerary high water mark is 5 feet. With a foot above the OHWM considered, the desired bottom elevation of the basin is 6 feet, resulting in a maximum depth of 11.5 feet. To set the bottom elevation of the basin, utilize the multi-polygon tool. Create a modification layer and draw a polygon in the desired location. Right-click the polygon, select Edit the Polygon Modification. This action opens a dialog box where you can choose parameters for the layer. For modeling a detention basin, choose the modification method, replace terrain value, and set a constant elevation of 6 feet. This replaces the existing ground elevation within 6 feet in the defined polygon. To confirm the terrain replacement, cut a section across the basin and verify the changes. The next step involves creating the 4:1 side slopes. To do this, right-click the modification layer, add modification line, and select high ground. The high ground is a polyline that should follow the outer boundary of the basin. To create it, export the bottom elevation polygon as a shapefile, then import it back as a breakline. Copy the breakline into the high ground modification layer within the RAS mapper, eliminating the need to transfer to another application. Once you have the line, right-click it and select high terrain value in the modification method. Assign a slope of 4 to the right side, 0.001 to the left side. This creates a 4:1 slope on the right side towards the inside of the basin and a vertical wall on the outside. Next, open the Edit Ground Line Modification tab. Adjust the station elevation data to follow the terrain elevation generally. If splitting the lines to ensure the ending elevation of one line matches the starting elevation of the next. With a higher value selected in the modification method, the side slope starts from the highest elevation existing ground and slopes towards the inside of the basin. To confirm the accuracy of the side slope, it's advisable to cut section across the basin. I recommend cutting multiple sections to ensure the correct modeling of the side slopes. If the slopes are not as expected, continue editing the station elevation and ground line modification tab until they match the design specification exactly. To model the inflow weir, it's crucial to determine its location based on the existing floodplain and flow pattern. In this case, the inflow weir is positioned closer to the river and within the floodplain. To locate the exact position, I recommend enabling the depth raster and RAS mapper and activate particle tracing. To model the inflow weir, begin by right-clicking the modification layer and selecting Add Modification, then click on Lines, choose Channel. Using the drawing tool, draw a line from the detention basin to the stream. Next, right-click the line and select Edit Line Modification. In the dialog box, specify the required bottom width and side slopes. Here I have set a bottom width of 50 feet and side slope of 3:1 on both sides. Choose the modification method as lower value. Set the elevation of the inflow weir in the dialog box. In this example, I have set the elevation as 12 feet at the start and end of the line. With lower values selected for the modification method, the terrain is defined area will be 12 feet or lower. This ensures that the weir profile is smoothly integrated with the existing ground without sudden jumps or drops. The outlet structure, in this case as a culvert, cannot be modeled as a terrain modification. It must be incorporated into the geometry. To add the culvert, switch to editing mode in the geometry section of RAS Mapper. On the culvert layer under ladder structure, draw a line from the detention basin to the river. Provide the desired culvert parameters and save the geometry. In the geometry window, further update the parameters as needed. For example, I have selected a 24-inch circular CMP culvert. Pay close attention to the upstream and downstream elevation. HEC-Ras requires culvert to slope towards the river, so the upstream elevation should be lower than the downstream elevation. You can see it here. You can estimate the upstream elevation based on the basin bottom elevation, culvert length, and a general slope of 0.2%. For added control, consider turning flaps prevent positive flow to block flow entering the basin from the river, or select no flap gate for bidirectional flow. If you are unsure about the culvert's flow direction, enable the directional arrow in RAS Mapper. If the arrow doesn't point away from the river, flip the order of the culvert coordinates points right here, where you see the X and Y. Here are some RAS Mapper visualizations that are useful to verify the proper function of the moderate detention basin. In the bottom left, you will find a section cut across the basin along the inflow weir using a profile line. This allows you to examine the basin's elevation profile. On the right, you will see the plan view of the model. When simulation activity, you can observe how the detention basin fills up through the inflow weir. Additionally, on the right, you'll notice corresponding increase in water circulation in the stream and the timing of water in the basin through the inflow there. This information is valuable for analyzing the effectiveness of the basin in managing water flow. Another visualization available in RAS Mapper is called particle tracing. This feature shows the direction of flow at selected time steps, allowing users to ensure that water doesn't enter or leave the basin at unwanted location. It's a helpful tool for verifying the accuracy of the model and confirming that water flow behaves as expected within the basin. Okay, now let's explore how to transform a wet bottom basin into a dry bottom basin. Unlike wet bottom basins, dry bottom basins require a longitudinal slope and pilot channel. Please note that the modeling for this transformation requires the use of ArcGIS. To create the longitudinal slope, use the multi-point polygon tool. Copy the basin polygon into it and choose the appropriate option as shown in the dialog box. Draw parallel lines to create points in ArcGIS, ensuring the elevation of the line closest to the outlet matches the basin bottom elevation. Calculate the elevation for subsequent lines using a slope of 0.2%. Create points along these lines at 50 feet interval using ArcGIS tool. Right-click on the control points and import the shapefile created in ArcGIS. This process will establish a longitudinal slope of 0.2% for the basin as demonstrated in the section. You can see the slope here, the 0.2%. To set the pilot channels in the basin, utilize the lines channel option. Draw a line representing the pilot channel from the farthest point in the basin to the outlet. For the start and end elevation of the pilot channel, provide a value lower than the basin bottom elevation at the respective location. This ensures proper drainage and flow within the pilot channel of the dry bottom basin configuration. A similar animation demonstrates the simulation of water entering and exiting the detention basin for a dry bottom configuration here. The outlet remains unchanged with minor adjustment in the elevation upstream downstream to accommodate the dry bottom basin design for the culverts. This visualization helps verify the functionality and effectiveness of the dry bottom basin managing water flow, as you can verify the time the water entered the basin and the time it is exiting out of it. This is again the particle tracing, which enables to visualize the flow patterns and direction within the basin, which also provide insights into behavior of water movement, ensuring that it remains contained within the designated boundaries of the basin. Now here I'm showing how to resize the basin without even changing the terrain. So you can easily resize the basin with very little effort within the RAS Mapper. So here I'm trying to reduce the size of the basin. To reduce the size of the basin, create another polygon at the desired location. So preferably from the end of the basin. Choose the higher terrain value for the modification method. Apply a constant elevation of, I applied 18.5 feet here, which is higher than the maximum water elevation in the stream and the basin. This will create a vertical wall that has reduced volume. So here it is the existing terrain and this is the new terrain. So you see all this area is kind of blocked off. So in this way, you have resized the volume of the basin. So you can increase or decrease the polygon size and determine what volume you require. So here is a simulation of the reduced volume of the basin that shows the area being blocked off where the polygon is drawn. So you can see that there is no water in this area. So this polygon is this pond is having very less volume now. So what these tools can do is these tools are useful that since it is within the RAS Mapper, you don't need a third party. These tools can be used to remove unwanted culvert crossing from the original terrain that are useful for modeling bridges or culverts to enable the input of deck, roadway, piers, etc. data, which you won't be able to do if you had a culvert in the terrain itself. Useful to create basins to determine required basin volume location. This tools allows for quick resizing of basins to determine desired mitigation volume, etc. But however, I would recommend using software such as Civil 3D or ORD to properly grade the basin once you have confirmed the mitigation volume that is required for your model. That's it. That's about modeling detention basin. If you have any questions, feel free to ask at the end of the presentation, or you can contact me at this information that I have provided here. Back to Hodo.
Yeah, Thank you very much, Thomas. Thank you. Please drop your questions in the chat, and we'll take them at the end of the second speaker's presentation. I'm going to ask Christy to introduce Zach, and then we'll go into the second presentation immediately. Thank you.
You are muted, Chris.
My apologies. I was just saying that I really appreciated Thomas's presentation. I feel like I learned a lot about that software, which I haven't used very much. So thank you for providing that overview. And now I would like to introduce Zach Labe. Zachary is a postdoc at NOAA's Geophysical Fluid Dynamics Laboratory and the Atmospheric and Oceanic Sciences program at Princeton University. He obtained a PhD in Earth System Science from the University of California, Irvine in 2020. His current research interests explore the intersection of climate variability, extreme events, decadal prediction, and explainable artificial intelligence. In addition to academic research, he is very passionate about improving science communication, accessibility, and outreach through engaging data-driven visualizations. And before I hand it over to Zach, I will just paste his Twitter a feed link into the chat for anyone who wants to see some of the visualizations that he does to help kind of improve that science communication piece. So over to Zach.
All right, great. And thank you for the introduction, and thanks for having me. I'm excited to talk about some of our work we've been doing and using sort of machine learning techniques to better understand climate change and variability. And I think I just want to first off start by saying machine learning is not new. So I realize it's increasingly becoming a buzzword to talk about artificial intelligence. In fact, it's on almost every night, it's on the evening news, something about AI. But the field of machine learning for uses in earth science, like climate science, actually goes back decades. And I've had a lot of fun actually diving into the literature that where machine learning and those words sort of first appeared. And one of the earliest papers I could find, at least in my field of meteorology, was back in 1964. And what you're seeing here is from this paper, and it's actually a very early form of a neural network. And essentially, this was a neural network that was used for weather forecasting. In particular, it was forecasting whether it was going to rain or not in the city of San Francisco based on sea level pressure. So I realize, in addition, to this buzzworthy, word of AI and machine learning, there's also other additional sort of jargon that goes about it, and sort of what are the differences between AI, machine learning, and deep learning. And then there's other words like things called unsupervised learning and supervised learning. And I'm not a computer scientist. I'm definitely a climate scientist by training. So I realize there are some, technical differences between these words, but for the broadest of understanding for my talk today, I'll sort of fall under this category of machine learning, deep learning. And I want to point out that many of you might not even realize it, but many of you are actually doing already machine learning in your work. So anything like linear regression or is a form of machine learning. It's called supervised learning. So it's basically anything sort of with a label. And then also a lot of you are doing things like unsupervised learning. So sort of clustering techniques, sort of to find patterns in your data also fall under this category of machine learning. And I think we're hearing more and more about it in sort of earth science and climate science in general is because we just have a growing amount of data. So in the climate model world, we run these intercomparison projects with lots and lots of climate models. And the most recent one, it was called CMIP-6, which produced something around the order of 30 petabytes of data and again, that's because, climate models are trying to encompass not just the atmosphere, but they're doing the ocean, they're doing the land, they're doing it, vertically aloft, down into the surface, like in your soils. And we have all these different experiments, and it's just accumulating more and more data. And right now, sort of the climate community is moving towards its next iteration of this intercomparison project. So that is called CMIP-7. And over the next 5 years or so, you're going to be hearing a lot about that. And how much data is going to be output from CMIP-7, I sure is a question. Perhaps it's another order of magnitude of data in terms of petabytes that we will have to sort through to understand climate change projections. And this is all really due to sort of the explosion of the use of high performance computing. So there's centers all around the world that are running these climate models. They're comparing them, they're outputting the data, and they're making, in most all cases, publicly available. And so now we need to figure out, okay, we have tons and tons of data that's growing, incredibly fast. We now need to find tools to sort of be able to evaluate all that data. And fortunately, there's an increasing number of also sort of community source, open access tools that are used as sort of part of the scientific workflow, not only for data analysis as like computational languages, but also just for posting papers and sort of processing those types of different things, storing it in data archives and such. And of course, one area like, in my talk is in this area of machine learning. And Python happens to be one of the programming languages that has some of the most tools for machine learning. And they're all sort of open source, community supported tools. Some of the ones that are listed here are really common for uses in sort of diving into machine learning. And you can see this reflected sort of if you look at trends. So I'm sure many of you have turned to Stack Overflow to look for coding bugs or questions that you might have. So I sort of like looking at this one interactive interface from the website that you can take a look at trends in different coding languages or different packages. So on the left-hand side, you can see trends and sort of the number of questions asked for different coding languages. You can see there's been a sharp increase, particularly in Python over the last couple years. And then on the right-hand side takes a look at some of the most common machine learning packages, where you can see starting in around 2016 or so is when there was a really, really sharp increase in sort of the use and, the number of questions that were being asked regarding some of these data science and machine learning sort of packages that are being used to evaluate all of this data. And there's this quote from a meteorology journal it's a couple years ago, but I still think it's quite relevant. And it says, today's weather climate scientist is far more likely to be debugging code written in Python than to be poring over satellite images or releasing radio songs. Of course, there is, an important use in having, experimental data, but I think all of us can agree, even if we work out in the field, that at some point we're going to come across sort of data sets that require them to be evaluated in some sort of coding languages or statistical sort of software packages. And for me, why have I started considering machine learning in my own work? Like I said, I'm not a computer scientist, I'm a climate scientist and meteorologist. And I think really the machine learning in general sort of falls under three different categories of ways we can use it, at least in my field. One, you can do things better. And what I mean by that is in, for instance, climate models, they're growing in the amount of data, they're growing in complexity, but some of these processes we still can't essentially resolve. So we have parameterizations, which are essentially empirical equations to sort of try to simulate these small scale features. And in many cases, there's being work that's exploring machine learning to try to do that better. And, we're having more and more of this high performance computing. So of course, our climate models are now taking longer to run because they're more complex, requiring more power. So can we use machine learning to speed up these processes? So, running 1,000-year simulation from a climate model doesn't take months, but perhaps it could take weeks. And the area that I'm, though, particularly interested in is less so on the model development side, but more so, can we use these tools from machine learning to learn something new in terms of our understanding of climate change and climate variability? So there's been a lot of work, particularly in the field of meteorology, for using machine learning to sort of better understand processes. A lot of these happen to do with severe weather, so designing sort of some sort of machine learning model to predict, the likelihood of a severe thunderstorm or the likelihood of hail or a tornado. There's also been some work on using machine learning for things like detecting thunderstorms from satellite imagery or outlining where cold fronts and warm fronts are. In addition to meteorology, there's been work in the field of oceanography. So there's a lot of good examples in recent years of using machine learning to, again, learn new science. So to better understand things like ocean currents or changes from climate change, like due to ocean acidification. But I think what's particularly interesting, maybe to me, is that there's been a bit less use of machine learning recently for sort of climate science applications. There's been some, so thinking of things like predicting El Nino and La Nina, or predicting other effects of climate change forcings like greenhouse gases or aerosols. But in general, this is an area where I feel there's a lot of room to explore. And so I wanted to start off real quick with, a background if you're not familiar with these machine learning techniques. And I think at its simplest form, the way I think of machine learning is that it's really just a statistical algorithm. So you take lots and lots of data, you put it into some sort of black box, that's your statistical model, that's the machine learning model itself, and then outputs a prediction, which you hope is some improvement over, perhaps simpler method. And one of the problems, with machine learning or reasons that people might be hesitant is sometimes trying to understand that statistical model, that machine learning model is challenging. It's sometimes referred to a black box. You don't really know what is going on there, especially if you're trying to understand physical processes. And I think it's really important when we talk about AI is to always mention about ethical concerns about AI. And you might think, okay, what are some of those for weather and climate? But in fact, there's been an entire institute by the National Science Foundation that's been recently developed just to think about how we can improve and consider trustworthiness in AI for Earth science. And to give an example, particularly in sort of the research to operations field of how AI ethics might come into a role for weather and climate, I want you to imagine, in the future, you are predicting severe weather. So what you're looking at on the right-hand side is a radar image near Washington, D.C. of a line of severe thunderstorms. And imagine you had some AI model that was determining how severe these storms were, particularly whether or not a tornado was going to impact the Washington, D.C. metropolitan region. And this AI model would then, issue a tornado warning, sort of yes or no. So the real concern is you need to have trustworthy models because the implications of issuing like a false alarm, you could evacuate an entire region that might not be needed. So I think really thinking about trustworthiness and ethics in AI is really critical, even in the earth sciences. And like I said, there's many, types of machine learning models. I'm going to be talking about sort of one area of them today that falls under deep learning. It's called artificial neural networks. And again, it all comes back to your data. So imagine you have some data points and you're trying to fit a line. So you're like a regression line. Really, all machine learning essentially is sort of an exercise in curve fitting. But one of your concerns, especially, if you look at this example, is that it could overfit. So overfitting is always a concern in machine learning. So a neural network basically takes some sort of input. Let's imagine you have inputs of X1 and X2. And they sum together in a node. And if you actually look at the formula for this equation so far, you might recognize it because it's simply multiple linear regression. However, what makes a neural network is something called this activation function. And you can think of this as just sort of some nonlinear term. And essentially, when you train your neural network or your any machine learning model, you're essentially just determining the weights and bias terms to, solve your prediction problem. There are many of these different types of nonlinear activation functions. I just listed three particularly common ones, but there's a whole field of computer science that tries to develop these terms. And you can add more and more of these hidden layers in these nodes where the weights and bias sum together, and that sort of creates your neural network. And they can get quite complex. And as you get more complexity or deeper neural networks, there can be many different pathways to sort of solve or output your prediction, which is why this black box term comes up, because it's, quite complicated to understand how all of these nodes are interacting with one another. So, okay, so far I haven't talked about climate. So, of course, we all know that the climate is warming. So I wanted to show, this is just a map of temperature trends over the last 30 some years for the yearly means. So essentially anywhere in red is warming, anywhere in blue is cooling. So you can see there's mostly warming, which is particularly amplified over land and over high latitude regions of the Arctic. So one of the concerns, as we see more and more increase in climate change, there has been some talk proposed of, in addition to mitigation techniques from reducing greenhouse gases, there's also been some talk of what would something like geoengineering or climate intervention do to the climate system. This is just a schematic of some of the different ways they're proposed. I'm going to be talking about a method called stratospheric aerosol injection, which basically means that aerosols or their particles are released in the atmosphere that essentially sort of reflect some of the incoming heat from the sun back out into space, sort of keeping Earth's temperature cooler. Of course, I'm not saying that this is something we should do, but the question is, if somebody, perhaps a private company or a government organization started something like this, would we be able to detect it? And that's the main question I'm going to be addressing using a machine learning model. Now, you might say, if you're familiar with like satellite data and remote sensing, you could argue that said, well, of course we could detect if somebody started it because you could look and see if there were more aerosols in a particular region. Yes, you could do that, but the question we're really interested in is how does something like this affect climate extremes, affect, regional patterns of climate change that impact people both in terms of weather and climate. And we can use climate models as a way to test this experiment to see what are some of the possible implications of this methodology. So, okay, let's take a look at what this looks like. So, no machine learning here, but I'm putting two images of Earth's temperature side by side. One side of this is coming from a world where we are experiencing climate intervention. The other side is a world where we are not. And if by looking at, side by side image, would you be able to tell which, simulation is which? At least I know that I cannot tell. So what about for a variable like precipitation? So now I'm showing precipitation over land. Would you be able to tell, which world is which based on just a map of precipitation? Again, for me, I still can't tell. Again, here, SAI means stratospheric aerosol injection, meaning which one is the geoengineering world. So you might say, if you're familiar with climate, well, we don't usually look at raw data. We often look at something like anomalies. For example, like when it's red, it's warmer than average, or blue, colder than average. So maybe, based on looking at anomalies, you might say, okay, that upper left map has a bit more blue. Maybe that's, the geoengineering world. But you can also see there's some blue on the right-hand side, upper right-hand side too. So it's still not necessarily clear. So the answer to sort of this thought question is that the one on the left column, that is this world that's experiencing sort of climate intervention to attempt to keep it cooler. So, what we're going to be doing here is trying to see if we can design a machine learning method to figure this out for us. So another way you could try to evaluate this is taking like averages over the region. So what you're looking at here is little graphs of the average temperature for different regions around the world, where the blue line, that's your sort of climate change world, and the red line is this world experiencing climate intervention. So you can see that, when climate intervention begins, which is starting at the dashed white line around 2035 in this experiment, you can see they diverge, but there's still some overlap, especially in the first decade. Now, if we look at something like precipitation, you can see that there's actually a lot more overlap. So, to my eye, it's essentially impossible to be able to figure out which is which. So this is where we turn to machine learning. So we're going to be using, two techniques to really try to answer this question of detection of climate intervention. And then we're going to use explainable artificial intelligence to figure out, what is happening or why it made its prediction. So what is explainable artificial intelligence? And basically, I call it an attribution method. And I want to give some quick examples here of what that means. So imagine you have some really simple neural network and you give sort of an image of a wolf. And the neural network says, okay, it's a timber wolf, it got it correct. But how did it make its prediction? And that's where the image on the right-hand side is from this technique. And it actually gives you a heat map where the brighter colors are saying that's where it looked to know it was a wolf. Okay, let's look at another example. This is an image of a volcano. So on the right-hand side, you can see that it looked around the outline of the cone of the volcano to make its correct identification. And one final example is, here's a shark. And again, the image where the brighter colors are is that's how it figured out. It looked in that part of the image to know it was a shark. I'll point out these methods aren't perfect. So here's an example of, it falsely identified this frying pan as a crock pot. But this explainability technique can still tell you where it looks. So you can figure out, where did it look incorrectly. And there's a whole, again, field of these types of methods. I want to point out that they're not perfect, and it's often recommended to use many of these methods. So here you can see a set of different methods for identifying a bird, and you can see some of these methods look different from one another. So turning back to our problem, the first question we're going to be asking is, if I give a map of temperature or a map of precipitation, is it coming from a world experiencing climate intervention or not? And that's the question I'll ask for global temperature. So the way to read this is that if the top row is red, that means it's correct. That means it's a climate change world. If the bottom row is blue, that means it's a climate intervention world. So you can see that after about 2040, it gets the predictions nearly perfect. But what about for other regions? So that was globally. What about for other regions, like in the Arctic and Antarctic, where there's a lot of variability in temperature? Again, here for the SSP245, that's the name of a climate change scenario. So as long as that row is red, it's getting it right. And for SAI, as long as that row is blue, it's getting it right. You can see that there's some variability, particularly for the Antarctic. There's a pretty poor prediction skill until about 2050, suggesting that predictions for the Antarctic are essentially less reliable. Now, if we look in a region like the tropics, you can see that those predictions are quite a bit better, so that the machine learning model here is able to detect much earlier which world is which. And so now we turn to this explainability method to figure out, okay, how did the model know? So what you're looking at here is maps of the explainability method, where on the left-hand column, that's for temperature, the right-hand column is for precipitation. So anywhere on the left-hand side, anywhere in red, those are really important regions where the machine learning model looked to be able to make its correct prediction. And if you actually dive into the details, try to understand physically, like, using, so our background understanding of the climate system, we find that the areas it's often looking are areas where it's called highest signal to noise. That essentially means that the largest amount of climate change relative to variability in that particular region. So many of these areas sort of make sense with our intuition based on using traditional methods in climate science, like signal to noise on the right, compared to the explainability method there on the left. So what about for precipitation? Again, precipitation's a lot more noisy, from place to place or day to day. So in this case, the top row, as long as it's bright green, that means it's right. And if it's brown on the bottom row, that means it's correct. So you can see that there's some mix and skill, but in general, for most years, this machine learning model is able to know which is which world. So lastly, in our case, so now that we know that this machine learning model technique can detect changes in extreme weather based on, whether it's stratospheric aerosol injection or not, we can now ask a neural network when it began. So let's pretend we have no information when this geoengineering started. Would a machine learning model be able to tell us when? And so I did this for multiple different regions around the world. And essentially the way to read this is that the x-axis is the year, the y-axis is the years since the start of geoengineering. So what we're looking at here is if the bright blue line is sort of following the one-to-one line that's in white. So you can see that there's some variability, but again, we're asking quite a difficult question here. Is we're asking just based on patterns from year to year of temperature and precipitation, can a neural network know when somebody started climate, climate intervention? And so we find for some areas, that it does quite well, like using information for the tropics, but other areas, like in the Southern Hemisphere, we see a lot less skill. So essentially, what we found here is that these machine learning methods are really good at detecting patterns of sort of temperature and precipitation, finding where the trends are the largest compared to natural variability. And in this case, we used it for this particular experiment. And I'll just point out that we've found that machine learning methods have been quite useful in a variety of different climate projection or prediction or even model evaluation techniques. And I think this really opens up an exciting area, to use machine learning as an additional tool. It's not the only tool, but it's just a new tool that we can use to better understand the climate system or better evaluate how our models are doing. So I realized I talked about a lot. So sort of my takeaway messages are, machine learning is not necessarily a black box anymore, and there are many different types of techniques that can improve our trustworthiness and understanding of what's going on in the black box. And like I said, machine learning is just another tool. It's not the only tool, and it's not going to replace any of our traditional methods, but I think it's just another one where we can attempt to learn new information. Like I said, it's no longer a black box, and I think we can learn new science from these types of different techniques. And I will end here, and now we can turn it over to questions. Thank you.
Thank you, Zach. Thank you also, Thomas, for the presentation before. I don't know if anyone has questions. They can leave it in the chat. I will start with one. I think this is for Thomas. Yeah, here from Christine. Is there a minimum basin size that can be used for modeling in this software?
Hey, Christine, there is no minimum basin size. You can use any size you want to model. It's pretty much flexible. Yeah.
Great. I don't know if, how do you want to read this, the next one?
Okay, yeah, there's a question here for Zach. Said, when using many more nodes and layers in the neural network, is it possible to track and output the pathways taken to generate each data point in a prediction data set?
Yes. So there are new techniques. So there is actually a difference. So I mostly focused here on something called explainable artificial intelligence, or sometimes I call it, attribution methods. But there's also an area of techniques called interpretable AI, which essentially you sort of design your machine learning model with the idea that you're trying to understand what's going on sort of at each step in the model. And these methods, these models are a bit harder to implement. And when you design one, you have to sort of go into already knowing that you want to design this type of machine learning model that's more, understandable. But it provides you a lot more sort of physical understanding. You could even maybe dive into causality. And I think this is just an area, even though it's been around in computer science, this is a brand new area for at least, in earth science, climate science. And I think we'll be seeing a lot more in that field.
Thank you. I see another question here. Maybe I'll go back to Thomas. How do you assess the effectiveness of a detention pond design using HEC-Ras?
So it's something that I showed you, the different visualization that you can have in RAS Mapper. So one thing to check is the RAS Mapper itself. You can see turn on the particle tracing to make sure the water is entering the basin and is exiting where it needs to be. Another would be drawing a profile line cut across the river and the detention basin. And you can see where the water surface elevation of the river rises. And at a point, it starts dropping water into the basin. And then you can see when it comes down. So you need to make sure that the water is entering the basin when the water elevation is at its peak. So if you have water entering the basin when your water elevation is low, it means that your basin is not effective. It's gonna accumulate water, then it won't be having enough volume to accommodate peak flow. So you need to detain your peak flow. So that's how you make sure that your detention pond is effective. And also you can draw a profile line downstream of the detention basin and check the flow from the existing and proposed condition, and you can check the lag that is there.
Thank you, Thomas. Another question, this one is for Zach. Have you come across any machine learning method that can responsibly boost a weak signal or reduce noise?
That's a great question, especially with the explainable techniques with those heat maps. You can get a lot of areas that look like noise that aren't necessarily physical. So there's increasingly, more methods to address sort of uncertainty, because oftentimes in your machine learning predictions, you really don't get any sort of metrics of uncertainty or a statistical significance like we're used to in other sort of linear methods. One method I like that's pretty simple to implement for those explainability maps is that if you actually sort of just shuffle your data, sort of scramble it randomly, which essentially just gives you random noise, and then input it into your neural network and then look at sort of these heat maps, you can actually get sort of a minimum or a maximum threshold for what would be sort of the magnitude of the significance of that sort of noise, and then apply that as some sort of threshold in your heat maps, so to make sure that anything greater than that threshold, must be more significant than random noise. So I think that's a pretty easy way of starting to get at least a little uncertainty information in sort of these explainability methods, especially when we're trying to understand regional patterns.
All right. Thank you. I think we have another question here for Thomas. He says, how does HEC-Ras handle multiple outlet structures or overflow paths in a detention pond?
So it depends on what kind of outlet structure you want. So basically, your outlet structure should be at a lower elevation, closer to the bottom of the basin, so that you don't exit all the water that is entering the basin at the peak flow. And if it is a culvert, you can use multiple barrels for the culvert within the HEC-Ras geometry window. You can have different options such as a gated structure, in which you can provide the stage at which time, at which elevation the water, how much flow is going to go out. If it is a spillway kind of thing, you can do a terrain modification just like what you did for the inflow way.
All right, thank you. Christy, do you want to take the question? I see another question for Zach. Just put in one more question for Zach in the chat.
Looks like we're just in time for our cutoff here. What kinds of information about the climate do we usually feed into explainable neural networks to teach them?
I think the fun part about this answer is you can input anything, so you can really have fun and be creative. At least that's how I think of science, is having fun and being creative. One common thread in what I input in is maps. It doesn't have to be global maps, but just maps in general. To me, one of the big advantages for machine learning is that you're sort of learning spatial information and perhaps nonlinear relationships across different regions. So I'm less excited about just inputting like a time series, where it's just, one dimension, but inputting multiple dimensions to see if we can learn, new insights across different locations. So I think the common thread for me is maps. I think, like I said, this is a new area. So oftentimes we're starting with like very basic climate variables like temperature, precipitation, but you can input really weird things and get strange things out of it. I've done drought metrics or land surface properties. So anyway, but the common thread is spatial maps.
All right, thank you.
Yes. Yeah, you
Do
can
we
go.
have any other questions? I don't see any other questions in the chat. Okay, thank you very much to our speakers. I'll hand it over to Valentina. You want to say a little more about YESS for the next 2 minutes before we end the webinar?
Yes, just for our participants, if you want to maybe watch again the presentations that will be in YouTube during this week, you can contact me if you want to ask any question, or I will also leave the emails of our speakers here in the chat box, so you can write straight to them. And I will just paste the emails. Give me 1 second. But yeah, after that, I think I don't have not much to say. Yeah, thank you all for your time. Okay, my computer is working bad, so I can't open my email to find the email address from Thomas. So Thomas, if you can write it down in the chat.
Yeah, I can do that.
My computer is doing something funny. But yeah, yeah, thank you everyone for participating today. And in the next month, we will have another webinar. So if any of you also wants to present, you can contact me, and we will allocate you in one of these upcoming webinars. So thank you also, Thomas and Zach, for your time and for your incredible presentations and your support for this first webinar. And also Chris and Hodo for your help organizing it.
Yeah, thank you very much, Thomas and Zach. I really enjoyed the webinar, and I know we have learned a lot. Yeah, so we just wait a few seconds to see Thomas. Okay, I see Zach's email, but I haven't seen that of Thomas.
I cannot access the chat. That's a problem. Right.
Oh, okay. Can you drop it in, then I'll just share it with everyone. Okay, great. Okay, great. I'll share it now. Okay. So yes. I just put in the emails for Zach and Thomas in the chats, so everyone can access it, so you can contact them if you have more questions about their research. And Chrissy, do you have any last words? We just end the webinar.
Thank you very much. Yeah, really appreciate it. This was a great way to spend an hour. So thanks for your time.
Yeah, thank you, everyone. See you.
Thank
Bye.
you, everyone. Bye.
Yeah, bye.